Welcome back to The Explainer. I am honestly so thrilled you're tuning in today because we're tackling something that is equally exciting and, let's be real, totally intimidating. We're talking about mastering LangGraph, specifically that massive leap from a safe, cozy, local testing environment straight into the chaos of real-world production. LangGraph is absolutely incredible for building these intelligent, stateful agents. But building the thing, that's just half the battle. Getting it ready for real users without it completely falling apart is where the actual engineering magic happens. Think about it for a second. You've built this amazing AI agent. It runs flawlessly on your laptop, but how on earth do you release it without it breaking the second a real person touches it? It's that classic, well, it works on my machine problem, but with AI, the stakes are just way higher. You're going from this tightly controlled script to a completely unpredictable production environment where literally anything that can go wrong probably will. So that's exactly what we're solving in today's Explainer. We're going to look at how you get your agent live, how to strictly validate its memory bank, and essentially how to prevent those catastrophic runtime crashes. We are bridging that gap from local write to enterprise. Okay, let's jump right into the infrastructure. When you move to production, you need a solid API and real agentic infrastructure to handle things like streaming, background runs, and obviously scale. For this, LangGraph Server gives us 4 distinct hosting routes. You've got their paid managed service, LangGraph Cloud. You can go with a self-hosted enterprise tier, or just bring your own cloud, like AWS. But the one I really want to highlight, which is honestly a game changer for developers, is the self-hosted Lite option. It lets you deploy on your own infra, test out your database and Redis, and it is completely free for up to 1 million nodes. It's basically the perfect sandbox to test your scale before you spend a single dime.
Now, you might be wondering, how hard is it to actually get this server running locally so you can prep for deployment? Surprisingly, it takes 2 simple commands. First, you just run pip install LangGraph CLI in your terminal. Next, you run LangGraph up. That's literally the whole shebang. Behind the scenes, Docker is pulling images, it instantly spins up a Postgres database to save your agent's threads, and it launches Redis for task management. Within seconds, you've got a fully functioning local server perfectly marrying production.
All right, so your backend is up and running. Awesome. But now you hit a new wall. These agents are complex, right? They're routing, looping, making decisions on the fly. Trying to figure out what your agent is actually thinking just by staring at terminal logs, it's kind of like trying to read the matrix. We desperately need a way to see what's happening under the hood. Enter LangGraph Studio. When you spin up that server we just talked about, you also unlock this built-in visual IDE, and it is basically a direct window into your agent's brain. You can visually track every single traversal through your graph, step by step. So if your agent starts a node, calls a tool, and then loops back around, you physically see that path light up on screen. You can inspect exact state updates, tweak messages, and test interactions right in your browser. It takes this completely invisible thought process and turns it into a tangible, easy-to-debug map. But look, just seeing the flow isn't going to stop crashes. So let's pivot to the first major danger of going to production. I like to call it the schema trap. Ask yourself, what actually happens when bad data somehow makes its way into your agent's memory bank? Because your agent's state is its memory, right? It's how it passes context from step A to step B. If that memory gets corrupted with garbage data, the entire logic of your agent just collapses. Let's look at why our standard Python tools kind of fail us here. Imagine your agent tracks a user's mood, and it strictly needs to be either happy or sad. If you just use a basic typed dict, there are absolutely 0 runtime checks. You could pass in a mood of mad, or just inject totally random, non-existent keys, and the system just accepts it, silently. No error at all. Your memory is just corrupted now. If you upgrade to data classes, it's a little better. It'll throw an error if a key is missing, but if you pass the literal word mad instead of happy, it still just ignores your rules and accepts it at runtime. This kind of silent failure is exactly what wakes engineers up in a cold sweat at 2 a.m. We simply can't have enterprise agents blindly swallowing invalid states. We need a strict enforcer to fix these silent failures once and for all. And when you implement the right fix, you're greeted with this incredibly beautiful message. Validation error. Input should be happy or sad. I know. Celebrating an error message sounds crazy, but trust me, in production, a loud crashing error right at the front door is infinitely better than a silent bug creeping deep into your pipeline. This error means our system caught the bad data and rejected it before the agent ever processed it. The hero making this happen is Pydantic. By using Pydantic models to define your LangGraph state schema, you are basically installing a highly aggressive firewall. Pydantic actually enforces your type hence at runtime. So if you set a rule that only allows happy or sad, and mad tries to sneak its way in, Pydantic immediately throws that validation error. It keeps your agent's memory bank absolutely pristine.
So the breakdown here is pretty undeniable. TypeDict catches nothing at runtime. Data classes catch missing keys, but totally drop the ball on bad values. Pydantic, it catches missing keys and strictly flags bad runtime values. Honestly, if you're building enterprise-grade agents in LangGraph, wrapping your state schema in Pydantic isn't just a good idea, it's practically mandatory for a safe system. Okay, so we've locked down the data types, memory is safe, but we are definitely not out of the woods yet. Let's tackle the next massive production risk. LangGraph has this awesome feature where it allows for powerful branching, which means multiple nodes can execute simultaneously. But think about this. What happens when two nodes run in parallel and they both try to overwrite the exact same piece of memory at the exact same millisecond? Bam! You get hit with this invalid update error. The graph basically throws its hands up in a panic, telling you a key can receive only one value per step. Think about it. If node 2 updates a value to 3 and node 3 also updates it to 3 at the exact same time, the system has no idea whose update to keep. So it does the only thing it can do. It brings your entire agent to a screeching halt. And this is exactly where state reducers come into play. You can think of reducers as the traffic cops of your agent's memory. Instead of letting nodes just aggressively overwrite each other, a reducer lays down the law on exactly how those updates should be combined. So if you annotate your state with a reducer function, say an add operator, those parallel updates are safely accumulated into a single list. Boom, no more crashes. Your memory just neatly saves both updates side by side. But we're in production, right? And production is completely unforgiving. Let's raise the stakes one last time. You've got your reducer set up, it's happily expecting lists to add together. But what if one of your nodes, or maybe a rogue user, passes a totally blank none value into the state? Well, your standard reducer tries to add a list to none, and you get slapped with cannot concatenate list to none type. Another catastrophic crash right in the middle of your parallel execution. So how do we fix this? Custom reducer logic. You can write a super quick Python function to intercept these updates before they ever get a chance to crash the system. The logic is beautifully simple. First, you just check the incoming parameters. Let's call the old state left and the new update right. If either of those happens to be none, you immediately convert that none into an empty list. Then, you just safely concatenate the left and right lists. Since adding an empty list to a regular list works perfectly fine, your parallel nodes are now 100% crash-proof, no matter what kind of weird blank data gets thrown their way. And honestly, just like that, you've taken a fragile local script and turned it into a robust, enterprise-ready powerhouse. You've got a solid handle on your server options, you're visually debugging with LangGraph Studio, your memory is locked down tight by Pydantic, and your parallel processing is safely handled by custom reducers. Your agent is now deployed, fully validated, and crash-proof. The architecture is solid, so the only question left for you is, what incredibly complex, world-changing agent are you going to build next? Thanks for hanging out with us. Keep exploring and keep building.